Hey guys, welcome back. So far in this unit, we have learned how to count atoms and how to balance chemical reactions. And we've talked a little bit about energy of reactions and what kind of factors can impact the reaction rates of these chemical reactions. Today, we are going to start a part of this unit where we start looking at the different types of reactions, okay? Because there are different types of chemical reactions that we have to know. Now, I do want to preface this by saying you guys have to basically pull all of your knowledge from not only this unit, but the unit that we did before this, which was ionic and covalent bonding, because you're going to have to use all of your skills and apply those over these next few lessons. Okay, so without further ado, let's get started. Today, we are going to be talking about synthesis and decomposition reactions. So after today, we should be able to identify what a synthesis and decomp reaction is, as well as use patterns to predict the products of synthesis and decomp reactions. All right, so there are 5 different types of chemical reactions, and over the next few lessons, we're going to learn about all 5 of them. Today, we are doing synthesis and decomposition. But over our next few lessons, we'll also learn about single replacement, double replacement, and combustion reactions. So those are the 5 types. Today we are just focusing on the first 2. So before we move forward and talk about what are synthesis and decomp reactions, I just wanted to reiterate this idea that we talked about in Unit 3. But as you guys are going through and doing these reactions, you're going to have to figure out what the products are, and you're going to have to balance the equations. So before we do that and learn how to do that, we have to remind ourselves that when we're writing these equations, there are 7 elements on the table that are always diatomic, okay? So that means that they never exist on their own as a single atom. They're always bound to either another element or they're bound to another atom of itself, okay? And we have to remember these 7 elements, because when you're doing these equations, if you have one of these elements by itself, you always have to remember that it has to have a 2 subscript, okay? So like, for example, if there is like an oxygen on your product side and oxygen is by himself, you're going to have to know that he's going to be O2, not just O. All right, so these are those 7 diatomic elements we have to know. It's hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Okay, so all of these are nonmetals that exist diatomically, so always at least bound to an atom of themselves. So you need to make sure these are written down in your notebook. And when you're doing your practice problems and your classwork and your quizzes and your tests, you want to have these close by so that you can remember these always are diatomic and they are always bound to at least one atom of themselves. Okay? All right, so now let's talk about predicting products for synthesis and decomposition reactions. So first, let's talk about what is a synthesis reaction. Well, to synthesize just means to create something. So if you remember from biology, protein synthesis, you are making a protein. Here we are making a new compound. Okay, so we're taking 2 elements and they are going to combine to form a compound. Okay, and it will look like this. So element A plus element B will yield a compound. Okay, so A plus B will yield AB, right? You can always tell when it's a synthesis reaction because you'll have single elements on the left and then you'll have a compound on the right. Now, to predict these compounds, you're going to have to use your knowledge of ionic and covalent compounds, how to figure out their charges from the table. Remember, we did all that in Unit 3. So if you struggled through that unit and you're still not sure about all of that, we're going to need to do some review ASAP so you can get a hold of these chemical reactions. Okay? So here's some examples. So this was the common form. So this is just the easy way to identify it. So let's look at some real world examples here. So here we have sodium and chlorine. will yield sodium chloride. Okay, so sodium, we have our metal. Chlorine, our nonmetal, so that's our indication that this is going to be an ionic bond. So we know we'll have sodium chloride. And sodium, remember when we're naming our ionic compounds, the name of the metal goes first, and then the nonmetal, and then we change the ending to IDE. Okay, this is why I'm saying you got to remember everything from our last unit, because if you don't, this unit, or at least these next few lessons, are going to be a struggle. Okay, at this point, that information should be, you know, pretty easy to recall, right? Because we just did it. All right, so then magnesium and phosphorus. So magnesium, again, a metal and a nonmetal, so we know this is going to be ionic, which will give us magnesium phosphide, right? Because again, we're just naming the metal first, and then the nonmetal, changing the ending to IDE. And then sulfur and aluminum will give us aluminum sulfide. Okay, these are all synthesis reactions. So again, 2 elements on the left will give us 1 compound on the right. Now, with synthesis reactions, there's a lot of different ways you can be tested on these, right? I could give you a reaction and ask you, what type of reaction is this? So literally just be able to look at it and say, okay, well, I've got starting metals as my reactants, and I have a compound as my product, so something has been created. This is synthesis. That would be the easiest way. Another way is that you could be given the reactants on the left and then have to predict the products, right, by using your either ionic or covalent rules. Then you would have to, there's also a possibility of being given an equation and having to do it all, right, having to figure out the products and then balance the equation as well, because at this point we know how to do all that. So everything in this unit is building on itself. Okay, so if you're struggling and are missing any of those steps, that's why it's going to be really important for you to let me know so we can get some tutoring in to aid with these reactions. Okay, so that's synthesis. Synthesis is very straightforward. Now let's take a look at decomposition. So to decompose just means to break down. So this is where a compound will break down into elements and or smaller compounds. So it's basically just the reverse of a synthesis reaction. Instead of having elements on the left and a compound on the right, it'll be flipped. You'll have your compound on the left that will break down into smaller elements or smaller compounds. So we would have our compound, AB, will yield A plus B. Okay, so we're just taking our compound and we're breaking it down into 2 elements. So now let's look at some real-world examples of this. So potassium nitride, right? This is going to be, again, ionic. We know we have potassium and nitrogen. Will break down into potassium and nitrogen. We just have to be able to identify the metal and the nonmetal, or the nonmetals, whatever the elements are. Basically, we just have to be able to identify the elements in the compound and then figure out what it will break into. So potassium nitride, we know that this nitride means it's just a nitrogen, because remember IDE is going to be an indication of a single element, right? So it's going to be potassium and nitrogen. And of course we go back to the nonmetal's original ending in an ionic compound, right? So potassium nitride, potassium and nitrogen. It's basically just the reverse of the ionic naming. Now, there are some special decompositions that I'm going to tell you about right here. You're not going to be heavily tested on these, but I do want you to be aware of them, okay? And these special decompositions just mean that there are specific products that are going to be formed when these particular polyatomics undergo a decomposition reaction, okay? So this first special decomposition is when a metal chlorate decomposes. So chlorate is ClO3, and that is a polyatomic. So these special decomps just talk about what happens when a polyatomic ion decomposes. Okay, so for the most part, you'll just be looking at single nonmetals that are bonded with a metal, but there are some cases where the polyatomic ions have a special decomposition. So a metal chlorate will decompose into a metal chloride plus oxygen. Okay, that means anytime, and this metal could be anything. It could be sodium chlorate, magnesium chlorate, whatever. It will always decompose into that same metal chloride plus oxygen. So if this was sodium chlorate, it would yield sodium chloride plus oxygen. The metal will always be the same on the left as it is on the right. So an example of this, we have barium chlorate. It will decompose into barium chloride plus oxygen. And again, if you were to need to give me the formula of this, you would need to use your polyatomic ion table and be able to figure out the charges from the table as well, do your swap, drop, and chop, and all that good stuff. And the chloride and the oxygen will always be a part of the chlorate decomposition. A second special decomp is going to be a metal carbonate decomposition. Carbonate is CO3, another polyatomic, and this will always yield a metal oxide and carbon dioxide, so that's CO2. So if we have an example here, potassium carbonate will yield potassium oxide plus carbon dioxide. So the oxide and the carbon dioxide will always be a part of the product, and the oxide would just be O, right? So if this is potassium, this is K, so KO and CO2, right? Again, at this point in this course, we should know how to figure out the formulas based on the names, and if we're still struggling with that, we need to make sure we go back and review. So again, the metal always stays the same, so the metal carbonate will decompose into a metal oxide plus carbon dioxide, which is CO2. So that means we'll always have CO2 in a carbonate decomposition. And then finally, the last one, we have metal hydroxides. Remember, hydroxide is one of the only exceptions to the IDE rule. So cyanide and hydroxide are the only polyatomics that end in "ide." The rest end in "ate" or "ite." But we have our metal hydroxide will decompose into a metal oxide plus water. So example here, we've got 10 4 hydroxide. That means the charge on 10 is 4. Will yield 10,4 oxide plus water. The charge will stay with the metal, okay, because this is still an ionic bond here with the 10 and the oxide. So this is not decomposing into two elements. It's decomposing into two smaller compounds. The compound here is 10,4 oxide plus water. Water is also a compound. The oxide and the water will always be the same, always a part of the product, okay? So that's the last special decomposition. The special decompositions you have to know about because they exist and is a part of the decomp reactions, but for the most part, we will keep it simple and we will stick to the individual, just one non-metal. So we won't look too much at the polyatomics, but we do need to be aware of it because it can happen. And so when we're doing these reactants, these chemical equations, we just need to keep some things in mind. Number one, remember your naming rules. Remember your swap, drop, and chop for your ionic compounds. And then, of course, at the end of everything, when we're doing examples, we always need to make sure our chemical reactions are balanced. Okay? These are the notes that are laying the foundation, but I will have a video in your assignment today where I show you examples of this and what will be asked of you on a quiz and a test. Okay, so once these notes are done, you can move on to that assignment and be sure to watch the example video, especially if you've got some confusion right now. As always, if you have questions, let me know, and if not, I will see you in that next video. Bye, guys.